computer. Right, so we are very happy to be joined by Ryan Briggs, who's an associate professor at the Guelph Institute of Development Studies and also the Department of Political Science. I just know him as a dad and as a cocktail and food aficionado. And for all the past few years, right, we haven't been doing these things. And so that's my understanding of Ryan's expertise. And I was shocked when he had this paper. He comes out and he says, well, actually, what you've all been doing is slightly underpowered. So very much looking forward to a very important paper. Thanks for joining us, Ryan. If you unmute yourself, I'll mute myself, and then we'll.
Okay. Success, I think. Maybe a thumbs up if people can hear me. Okay, we got some thumbs up. Cool. Thank you for having me. So this is joint work with Vincent Arel-Bunduk and Krista Kuliagos, T.D. Stanley, and Marco Mendoza-Avina. And yeah, what I'm going to do is describe why I've come to believe that almost all research in political science is like very radically underpowered. I'm not happy about this result. I'm didn't think of this as naive, but like a real believer in social science to actually do like important things in the world. So if anyone can convince me why this is wrong, I would like really appreciate it, because like I'm actually really bummed about this. So what I'm going to do is just start by describing a little bit of basics on power. This is going to be familiar to a lot of people, but I do want everyone on the same page before I get into the actual results, and then I'll spend most of the time on the actual results and lots of time for Q&A. I guess I don't know how we'll do it with the chat, but like if you have questions, just like please ask me.
So
you're gonna, okay, perfect.
Here if people in the room want to.
Yeah, don't wait if there's anything that's confusing, please. Okay, so what is power? So there's like a number of ways that we can think about this. Your kind of go-to definitions are going to be the probability of, well, it's okay. The math is going to be a little, oh, interesting. It's rendering differently on two screens. Anyways, the probability of rejecting the null if your research hypothesis is true. Second one is going to be one less than the probability of type 2 error. If you're actually, like if you think in code, then this function will give you your power. So all this is going to do is take two arguments. We'll just set the alpha to 0.05. It's going to take two arguments, the standard error, and then what I'm calling here the truth, but basically the effect that you think is going to exist, right? And this first line, the critical z, is just going to give you your 1.96. The second line is just the truth divided by the standard error. So you're just rescaling that. It's where you're going to set that like sampling distribution that you'll draw from. And you're going to figure out how much of that sampling distribution is going to be out in the rejection zones in either tail. You're going to add them together, and that's going to give you your power. So the normal thing that we talk about sometimes, you know, for 2.8, standard error is away from 0, then you have 80% power, and so 2.81 gives you your 80%. I don't really think in code that well, so I think graphically. So here's another way to see this graphically. Null distribution, standard error of 1. We've got our sort of 0.05 rejection zone starting at around 2. So a test with 50% power is going to be a test where you just center that sampling distribution like right on 1.96, right? Then half the time that you pull from it, you reject the null. Half the time that you pull from it, you do not. Where this gets interesting is when you have very, very low power, and especially if you have very low power and some kind of selection on statistical significance. So if you just have really low power, this is 6% power. In this world, you're just usually not going to reject the null, and like in a way that's fine. If you do have a significant result, then you're either going to have the wrong sign, which is going to happen in this case about 20% of the time, or you're going to have effects that are way too big. So, you know, these sort of on average are going to be 8 times too big. We've known this for a long time, right? This is like standard. If you've read Gelman's blog anytime in the past like 15 years, this sort of message has just been like hammered theoretically. I don't think it's sunk in. And I'm going to demonstrate empirically that it really hasn't sunk in. So our big contribution here is not really any of this. This is well known. It's to actually gather the data and look and like see what power looks like. So what we want to know is two things. The first one is just how well powered is political science research? Do we have like reasonable power to detect plausible effect sizes? And the second thing that we want to know is, do we as political scientists have like an accurate picture of power? Do we understand how good or bad power is, or are we just kind of flying blind? So we're going to do two things. The first thing is we ran a survey. We surveyed everyone who published in the main methodology journal in political science, which is political analysis. From 2010 forward, we sent out, or successfully sent out, about 500 emails. We got a pretty good response rate. 131 people responded. And we asked them, if you imagine the percentage of hypothesis, think about all of the hypothesis tests that were published in the top 50 political science, international relations, and public affairs journals. Just imagine all those hypothesis tests. Think about plausible effect sizes. What fraction of those do you think had 80% power to reject the null? And then what fraction of those do you think had 50% power to reject the null? And I don't know, like, this isn't like a glowing endorsement of what we think of our own research. So 2/3 think that we have at least 50%, or sorry, of all the respondents, they think 2/3, Let me take a sip of coffee here. On average, the respondents think 66% of tests have 50% power, and they think that 43% of all of the tests have 80% power. That's just averaging across all the respondents' answers. Yeah. Okay. We also wanted to figure this out for ourselves. So this is a little bit tricky, because if you think about that function that's going to return power, we need to provide two arguments. One is the standard error, which is really easy. You can just get that from like every reported table. But the other thing that we need is like the true value out there, which you don't know, and is always the hardest part if you're doing a power calculation. And you kind of read the surrounding literature, and then you're like, that's probably an overestimate, it's probably lower, and you try to like hash this out, right? But it's difficult, and we're certainly not going to be able to do this better than the authors of all of these papers across all these different areas. So what we did is we leaned on meta-analyses. And so we gathered data on every meta-analysis published in political science and international relations and public administration since the year 2000, where we could find data. There were about 80, the details are in the appendix. There were about 80 papers total. We could find data on 46 of them. Those 46 published papers included 351 meta-analyses. To clarify, because that should seem kind of weird, there's two reasons that seems kind of weird. The first one is our definition of a meta-analysis is you've got to have the same independent variable measured the same way, same dependent variable measured the same way, and then the treatment gets applied in the same way. And so it's very common for one paper to have multiple meta-analyses by that definition. Also, we had one just epic paper from the conflict literature that contributed, here, let me check my notes to get this right, 259 of the 351 meta-analyses, though many fewer hypothesis tests. I will show you later, it does not matter at all if we include or exclude this paper, but there was one kind of wonky paper, and that's what explains that number being so big. In total, we had 16,000 hypothesis tests after cleaning the data. So what we did then, if you think about like the main point of a meta-analysis most of the time, the main point is to give you basically an estimate of the true actual effect across all these different studies. And so we can use the fact that authors have grouped together these similar studies to come up with a good estimate of the population mean effect, which I know I shouldn't do this, but I just keep thinking of as basically the truth. And so if you want like an intuition as to how this would work, just imagine that you have a meta-analysis with 10 estimates, and you got their standard errors. So you're going to use some meta-analytic technique to basically just take a fancy average to give you one number, which is like our best guess as to what's actually going on when we kind of average across all of these 10 studies. What we're going to do then is say this one number, this is our like truth value, and we have the standard error for each of those 10 tests. We're going to ask like how well powered are those 10 hypothesis tests to actually detect the meta-analytic effect from that meta-analysis. So that's the two things that feed into that function. There's no like obviously right way to do what amounts to fancy averaging to come up with a meta-analytic effect, so we're just going to do it 3 different ways. The biggest, this might sound kind of circular to you. It kind of is. And the biggest problem with this is if there's bias in the reported results, and there's going to be bias that feeds into the meta-analytic effect. It seems to me that the most likely form of bias is going to be publication bias, where people that get insignificant results don't end up publishing them. And if you think about what that's going to do, like if you imagine putting those estimates along the line, we're going to not have enough of them near 0, because those the ones that come up that way don't get published. What that's going to do is basically pull our meta-analytic effect away from 0. And if you think back to the graphs of power, that's going to make power look too good. Right? We're going to have a sort of truth effect or a population mean effect that is too big because we're missing these near 0 results. So I think the takeaway there, and we can talk about this in Q&A if you want, is we are likely going to overestimate power. Okay, I will explain this quickly because I'm sorry the math hasn't rendered properly, but we're going to calculate population mean effects in 3 ways. The first way is just weighted fixed effects. After that, just don't worry about it. It's a precision weighted mean. So yeah, and that's the first one. Basically doesn't correct for publication bias at all, or it corrects for it only a little bit with the weighting, right? The second way that we're going to do this is we're going to start with the weighted fixed effects results, calculate the power of each test using the weighted fixed effects results. Then we're going to pick only the coefficients and standard errors that reach at least 80% power. We're going to calculate weighted fixed effects again on only that subset. If you think that the sort of high standard error, high variance tests are more likely to be like manifesting some kind of selection on statistical significance, then this should reduce publication bias. And the final way that we're going to do this is called pet piece. It's the precision effect test and precision effect estimate with standard error. I think I got that right. The intuition here is if you take, imagine a scatter plot where you've got the coefficient estimates on the y-axis and you've got the standard errors on the x. So for some structures of publication bias, you're going to have a positive relationship between the estimates and the standard errors. And so if there is no publication bias and you have a kind of funnel that is kind of like, I don't know, a wedge of pie coming out, you'll have a flat line, everything's fine. If you have publication bias, the slope of that line will be either positive or negative. And so what you can do is take the intercept, and that's giving you a way to unwind some of that publication bias. So we're projecting back and saying, if the standard error were to have been 0, then what would the coefficient be? This will only work with like some structures of selection on statistical significance, but they may be common. And so this will unwind some of that. We don't have to pick whatever one you kind of like the most. We're just going to show all of them. And we also did like 10 other ones. They all show the same thing. These sort of span, the way that we're thinking about this is that these really span from the least correction to the most aggressive correction for publication bias. And that's why we picked these 3. Okay, so why am I talking about publication bias so much? The reason for that is because I think we have a lot of it. So this is showing absolute Z statistics for every single hypothesis test that we have in our sample, so 16,000 and some. The bin width here is 0.05 of a Z-score, and we're marking significance thresholds at 95% and 99%. This is a bummer. It's kind of what you expect, but it still hurts. It looks similar to people in economics have made pretty similar graphs. They look pretty much the same. I will note both the spikes that are disappointing at 95% and 99%, but then also the humps after them. It's really hard to explain a pattern like this in our published results, absent selection on statistical significance. So we probably have that. Who knows if it's p-hacking or it's journals picking significant results, or it's like all of these things put together. It doesn't really matter for our purposes. We likely have a lot of this. So again, what this means is we're going to be overestimating power, most likely. Okay, so I don't need anyone to like raise their hand or shout out answers, but I do think it's helpful to like anchor your thoughts here before you see the results. So just like, I'll take a sip of coffee and everyone can just like take a second. And 80% is often our like benchmark standard for power. Just think for yourself, what fraction of tests do you think had 80% power in our sample of 16,000 and some tests? And in case you want a little bit of help like anchoring, the expert survey, on average, they thought 43% of all of the tests would have 80% power. Okay, so here's the answer. The quick answer is it's 10%. And let me explain kind of what's going on here. So the black dots are from the expert survey. The box plots are just marking the quartiles. The x-axis has the power level. Each line is a different way of coming up with our population mean effect estimates. And the y-axis is the share of all estimates that reach at least that level of power. So we see on the 80% power line, we got all the expert surveys. A few people in our survey did get it right, but most of them.
I can de-identify them.
I have not. We are not able to do that. Please don't cause any more problems between me and my IRB.
Because I can guess at least one of them.
My personal like sort of dark favorite here is the 50% power ones. So basically the answer is something like 1 in 5 tests reached 50% power. Every single person in our expert survey overestimated this. Some by only a very tiny amount, but many by quite a bit. I also would have thought that it was higher up front. I thought things were bad, but I didn't think they were this bad. And then the real pain starts at the low end. So we start at 6% power, because like 5 is, they're all gonna be that, right? That's by definition. So we're starting at 6% power and running to 99%. And so, if you kind of eyeball where 10% power would be, it's around half. Yeah, so I mean, this is our core result. I'm gonna kind of describe this in a bunch of ways. If anyone has questions at this point, I would take them before kind of like getting into nuances, but if not, I'll just keep going.
So in these meta-analyses,
Yes.
are you restricting to only hypothesis tests that were the main test of the paper? The main theoretically motivated test?
Yeah, that's a great question. So this is an unfortunate answer to a good question. We are trusting the meta-analysis authors with a lot. We do some data cleaning on areas where we can. So for example, sometimes the paper will report like the coefficient, the standard error, and a p-value. And if those don't agree, we're taking those in. And so we were able to detect some errors, and some of them we went in and fixed by hand by finding the original. Whatever. Some of them we fixed. Most of them we dropped. So our data is, I think, a little bit cleaner in that like numerical sense. But we are not digging into it at that level of detail. I'm guessing the question is because if you have a paper test 3 things, it's powered to detect the first one, but they just grab them.
Yeah, powered and designed it.
Yeah,
and set up,
exactly.
and that's what they care about. And yeah.
Yeah. My hunch is that, like, knowing what political science research typically looks like, my hunch is that is not a major concern here. I'm hoping to do a similar paper on development interventions that are all basically like randomized control trials. I think it will be a real problem there. And I think we have to go into a much closer level of detail and basically just say, pick the most highly powered result per paper and just go with that. My hunch is that's not going to bite very hard here. It's a really good question. No, okay. So how bad is this really? I think it's really bad. Okay, so first of all, like using our most generous method, median power across the full sample is 10%. Like half of all of them have less than 10% power. This is really getting into that like danger zone when you imagine those 2 overlapping distributions like I showed earlier. And if we have selection on statistical significance, which we do because we all saw the graph, then what this means in theory is we are going to have a lot of results that are in our published literature and statistically significant and are either way inflated or the wrong sign. We can look at this empirically. We kind of know this from theory, but we can actually look at this empirically. So let's do that. We have 16,600 hypothesis tests. Around 8,000 of them are statistically significant, because we're really good at guessing the stuff that's going to work out. Of those, so just focusing on the statistically significant results, and only using the most generous method, right, where it will have the largest effects because it's not really correcting for publication bias. 15% of the significant results have a different sign than the underlying meta-analytic effect, which is around what you would expect from theory. And then of the remaining 85% that basically have like the right sign, at the median, they're 3 times too big. So I think the way you can basically think about this is if you just pick a political science journal that's published sometime over the last 20 years and just flip to a random page and put your finger on a statistically significant treatment effect, then you should imagine you've got either a 15% chance that it's the wrong sign, so the whole paper is written around this positive effect, but it's actually negative, or if it's the right sign, then it's probably something like 3 times too big. And that's that's what we're working with. Yeah, and again, like all of this looks worse if we use the methods that correct more for publication bias. Okay, so you might think one potential problem here is I'm talking about the political science literature, but we don't look at the political science literature. We ask our survey respondents about the political science literature, but we gather data on meta-analyses. So maybe there's a problem generalizing out to the whole literature from meta-analyses. We were worried about this too. My hunch was that it was going to be the other way around. The stuff that ends up in meta-analyses might actually have power that's a little bit higher. It's part of these like research programs where everyone's working in the same area, they might have more awareness, but who knows, right? I would say that. So we just asked our survey respondents if they thought that hypothesis tests that end up in meta-analyses are going to have higher, lower, the same power as the tests that just never end up in a meta-analysis. And yeah, they came down kind of where I came down. 3/4 of them thought that the tests in meta-analyses would either have higher or the same power as tests that don't end up in meta-analyses. So I don't know. I don't think that's causing any bias that's like a real concern. We were still kind of worried about this and honestly just kind of curious, like, are there other biases that are creeping in that are causing us to understate power? And so at Vincent's good idea, we just took all of our population mean effects generated with the most generous method. We just multiplied them all by 5. Just generated a fake data set with all of these vastly inflated hypothesis tests, population mean effects. And then we just ran the analysis again on this data. When you do that, about 1 in 3 tests still don't reach 50% power. So even if we're missing some like truly gigantic source of bias, it's still probably the case that like a very large share of our literature is just radically underpowered. The last robustness test thing I'll show you here. We also worried a little bit about like atypical meta-analyses, mostly because one paper contributed so many meta-analyses. That seemed really weird. And then you're like, what other ones are in there? And so this is showing a version of the graph that you saw before, only using the weighted fixed effects results and just sequentially withholding one full meta-analytic paper's worth of data at a time. And then plotting these really thin lines, so that thick line just emerges from overplotting. The results don't move much when we sequentially withhold any one paper. They don't move much when you sequentially withhold any 2 papers. And then my computer was sad, and so I stopped, grinding through more and more combinations. Yeah, so I think like in summary, like we really need more power. This is like a pretty serious problem. I'll conclude with just 2 kind of ways of slicing into the data. We don't have a lot of data on like at a per hypothesis test level, but we have a little bit, and so we can add a little bit of like interesting nuance here. So here's the first kind of interesting cut into the data. What I'm doing here is showing a histogram with the median power per meta-analysis. So there's 351, add this up, you get 351. And so what this is showing is it's not the case that like every, say, research area in political science is equally underpowered and we're all just kind of underpowered. Most have incredibly low power, between 5 and 10%. But there is this like very large minority of work that is very highly powered. I think there are like a number of explanations of the sort of what's going on in the discipline to generate this. We can talk about that if you want later, but I will say this is very similar to a result in economics. So whatever explanation we have of this is something that seems to exist at least across another social science. And then finally, it looks like power is increasing over time. So that's nice. Let me like put a little bit of cold water on this. So every hypothesis test, basically, I think maybe a couple of percent of them don't have a year, but almost all of them had a year. So we can make this. There's not a lot before 1990, so I'm just not showing that. There's also not a lot after 2005. So I don't trust this steep area at the end at all, and I don't think you should either. I think it's very possible that with a few more years of data, that will kind of flatten out. The red line is showing like a smooth mean. And so what's really pulling it up over time is the inclusion of a lot of very highly powered work as you move. So mean power goes up over time from something like 0.15 or 0.2 to something like 30-ish or 35%. It's mostly being pulled up because of more papers at the very top end of power. Median power does go up over this period, but much more slowly. So again, if you're trying to think of like what's going on in the discipline, like we're having more people publish more very highly powered work, but like that median paper, it's improving here, but nowhere near as much as the average. Yeah, so, okay, so 3 takeaways, and the first one I think is the most important. The first one is I think that political science research is just like radically underpowered. The second one is I don't think this problem is appreciated by the discipline. We really don't have a good sense as to how bad things are out there. And then the third one, to end on like a bit of a positive note, is we're really excited by some stuff that people are doing to address this problem, and they have been doing for a while. So I'll just flag 3 things. The first one is there's been a real push in, I've been aware of it the last couple of years, to get people to use within subjects designs and to try to like make us less concerned about bias, which I think has traditionally held us back there. You know, classic trade-off here, but within subject designs, you're just gonna have way more power and you don't need more subjects. And so without much more money, we might be able to just really dramatically increase power. The second one is people, I think, have been taking measurement more seriously. So things like the use of indices to reduce measurement noise is a really big deal because all of a sudden you can radically increase power with, again, not having to massively increase your sample size. We get exactly the same. I think that's a really big deal. And the third one is anything that allows us to get an unbiased meta-analysis of even low-powered studies. So I'm thinking of things like results blind review, or any ways that we can get sort of file drawer results out there in a format that everyone can access. I think that's a really big deal because realistically, we're probably going to keep having low-powered studies for at least the foreseeable future. That's fine if all the results are published and we can just do a meta-analysis on them. That's not the world that we're in right now, but like results blind review would get us there. So I think that's all really good stuff that people are doing to help to ameliorate this. Yeah, so yeah, thanks for.
Do you want to stop sharing?
Sure.
Do you want to turn on your video?
Sure.
And then I'll turn on. Yeah, there we go. So does anyone have any questions? You can think about it for a moment while I ask Ryan our newly traditional first question for this term, which is if you could have an idealized perfect data set. Taiki says, I will give you perfect information, perfect data set of one thing. What would it be?
Okay, so I feel like I should give an answer that's something about like some kind of utilitarian calculus thing so that I could, put this out there and allow people to do more good stuff to make like more good people happy. I don't have a well-formed version of that, and so I'm just gonna have to say like there's so many combinations of cocktail ingredients, and I don't have a good sense as to like how those mix and introduce interesting delicious flavors. So I'll go with a cocktail combination data set. There's a lot of combinatorics there.
That's very good. All right, I'll stop recording.